Usually when we solve a complex set of equations like we did in class, we need a little more than just equilibrium constants. In our calculation, we assume that there is enough atmosphere that the carbon dioxide isn't going to decrease as it moves into water. In most systems, we can't make that assumption, but we might know the total formal concentration of a species. For example, if I make a phosphate buffer, I know how much total phosphate I put in, and it should be equal to the phosphoric acid plus the dihydrogen phosphate plus the biphosphate plus the phosphate. This type of equation is called a mass balance equation, and it can help us to find more equations for our many unknowns in solution. Similarly, we know that we should have an overall balance of zero charge for a solution. Our solutions don't carry a net positive or a net negative charge, which means we should have the same amount of positive and negative charge if we total up both types. This we actually did in our coral example. For the phosphate solution above, we would have the H+ concentration, our only positive charge, equal to the dihydrogen phosphate plus 2 times the bisulfate because it has a -2 charge, plus 3 times the phosphate because it has a -3 charge, plus the hydroxide concentration. Again, this is called a charge balance equation. Like we talked about in class, we can often find concentrations for many different species if we know enough about the solution, like we did for dissolved carbon dioxide, aqueous carbon dioxide, carbonic acid, bicarbonate, carbonate, and calcium. You need to have as many equations as you have variables. If you know that a species will almost be entirely in one form, you can assume these forms don't contribute to charge or mass balance equations. But you can't take them out of equilibria equations since they are multiplied and no equations will work with a zero value substituted in. If you did assume all of the, say, phosphate was actually biphosphate, you'd want to verify at the very end that that was true. So you might be able to say that the concentration of phosphate is essentially zero, but you'd want to go back and check to make sure that's true using your equations once you've finished. The ladder diagrams we had talked about before can be really useful for helping us to know what the most likely forms of a compound are in solution. Let's start by listing all the pKa's of this species, our MSG pure, on a ladder diagram. Then we'll draw the structures for each species. There should be 4. So there's all the pKa's on the ladder, and when we list them out, we have these 4 species. The amine is the highest pKa, so it's the first proton to be exchanged. Amine pKa's are always for the ammonium to amine transition. If we go from amine to amide, the negatively charged nitrogen, that's going to happen only at incredibly basic conditions. It might not be apparent immediately which form of MSG will be dominant, but think about the charge balance for this. The H+ concentration should be relatively low compared to the 0.5 molar that I'm saying that we're putting in, or the 0.5 formal of pure MSG, unless the solution is really acidic. The MSG without the sodium has a -1 charge. If we go more negative than -1 charge, we'd have to have H+ to balance it out, which would be unlikely because more negative would imply we'd have a more basic, not a more acidic solution. There can't be much of anything more basic than a -1 charge because there wouldn't be enough H+ to balance it out. On the other hand, there can't be much of anything more acidic than a -1 charge because you need to have hydroxide to balance it, and again, that's unlikely in something that's more acidic. So we're almost completely certain that we're going to have the second structure down, which has a net -1 charge. If I assume that this is most of the mass, I can just use the Ka's to find the other values and then check and see if I was right. Last lesson, we derived the Henderson-Hasselbach equation, which is just reforming the definition of a Ka by taking the negative log of both sides. What this makes clear, though, if you think about the math, is that when the A- and HA concentrations are fairly close, the pH won't change very much as we add acid or base. Think about an equal ratio of A- to HA. We think about A- and HA having the same concentration, the value inside of that log would be 1, and the overall log would have a value of 0. So we'd say at that point, our pK and our pH are the same, when the HA and A- are the same. But if we changed half of the HA that we had to A-, say we start out with a concentration of 1 to make it easy, then we'd have 1.5 A- to every 0.5 HA, or we'd have a value inside of that log of 3. The negative log of 3 is about negative 1/2. Since the pKa can't change, that means the pH will go up a half unit to compensate. So even if we changed half of the acid to base, the pH would still only go up by about a half unit. This is a phenomenon known as buffering, and it can be really useful for controlling the pH of solutions. A pH buffer is always a conjugate acid-base pair, and it can buffer to about 1 pH unit on either side of the pKa. So if we have a pKa of 4, we'd expect the buffering region to go from 3 to 5-ish. Once the acid and base concentrations aren't close, the pH will change quickly and it will no longer buffer. We typically keep our buffers at 10 millimolar or greater, because if the buffer is on the same order of magnitude as the acid that we're trying to add and resist pH change for, it won't actually work very well. We'll make buffers a lot in the lab. In fact, you've already made a buffer in your third lab. We can either just start with a conjugate acid and add base until the pH is right, or we can start with a base and add acid, or we can try to add the right ratio of conjugate acid and conjugate base using the Henderson-Hasselbach equation. I usually start with a conjugate acid or base and add H+ or hydroxide to adjust. When you made the buffer in lab, you actually use citrate as the base to add to the acid and adjust. Some systems can have multiple pKa's, like the carbonate system. The first pKa in the carbonate system is from carbonic acid to bicarbonate. In this figure from Manahan, it talks about carbon dioxide instead of carbonic acid, but you know those convert. You can see the place where the lines cross, first between carbon dioxide and bicarbonate, right around pH 6.4. This is the pKa. When the carbon dioxide is being converted to bicarbonate, mostly from around pH 5.4 to pH 7.4, we're in the buffering region for that lower pKa. And then if we look at the next place where it crosses, we see from 9.3 to around 11.3, another buffering region centered around that second pKa of 10.3. And we can see that in between these buffering regions, we have a section where the very large majority of the carbonate, or the carbon system, is bicarbonate. Like we saw in our in-class problem, we mostly sit in this range. This is actually also true of your blood, which has the same bicarbonate buffering system as we see in oceans and surface waters. Because the waters of our world and our life are not just water, pH only tells part of this story. The bicarbonate that ends up as part of the water prevents the water from being swayed quickly to more acidic or basic because it's a buffer. We use the concept of alkalinity or acidity instead of pH to account for all this built-up capacity to resist change, a buffering capacity. So a solution with pH of 7 that's buffered will be far more acidic, that is able to resist change by hydroxide. It will also be far more alkaline, again able to resist change by H+, than we'd see for an unbuffered solution of the same pH. So when the ocean pH goes down, that's going down not just as acid gets added, but an entire buffer system gets added on top of that. A buffer is typically prepared for pH, but we can actually generalize this concept to think about buffered ligand or metal concentrations using the PL or the PM, the power of the ligand or power of the metal, and the formation constants, or we can even talk about buffered redox potentials using the potential values, the E. A buffer consists of two easily interconverted species. The buffering range extends about 1 P unit, whether it's PL, PM, or E, to either side of the equilibrium value. We are just about to reach our first major point of divergence between environmental chemistry and quantitative analysis, ionic strength. While the majority of this concept will be in the next lesson for 202, and not at all in 333, I wanted to establish a conceptual understanding of ionic strength. First, let's agree that the molecules that we show here exist on a continuum of polarity, from completely nonpolar on the left, going through polar covalent, hydrogen bonding, weak ionic, and eventually to strong ionic bonds. And let's also agree that like dissolves like. So for reasonably small molecules, polar covalent molecules, molecules that hydrogen bond, and weak ionic molecules are all similar enough to water for water to dissolve them. So far, I don't think I've said anything controversial. The interesting part comes when we have ionic compounds that dissolve in water. We call these electrolytes because they can carry electricity in water. Electrolytes can either be strong, that would mean they dissolve completely and therefore carry more charge, or weak, they dissolve only partially and therefore only carry charge on a small portion of the molecules. But what happens to the polarity of water once we start dissolving a lot of strong electrolytes? It should become more polar since a large portion of the molecules are charged. Those of you who took the whole year organic might remember times that we used salt to separate water from small polar molecules. We called it salting out. This is because the addition of polarity has shifted the solubility of our molecules so that the less polar molecules can no longer stay in solution, while at the same time we can dissolve more polar molecules. We quantify this phenomenon with the idea of ionic strength. Ionic strength is pretty much the total amount of charge in solution. It's relatively easy to see in this graph that as salt concentration goes up from left to right, the ionic strength would as well. But notice that each of the three equilibrium constants, the Kw, a Ksp, and a Ka, all change drastically at high ionic strength because the addition of salt has actually changed the properties of the solution. Calculating ionic strength is easy. Ionic strength is given as the variable mu. We take each ion's concentration by its charge squared, that's the Z value, and we add them all together and divide by 2. Dividing by 2 benchmarks ionic strength so that it's the same concentration if we have a +1 and -1 ion pair. So for example, a 1 molar salt solution would have 1 molar sodium times 1 squared plus 1 molar chloride times -1 squared. And then we divide the whole thing by 2, and it would give us a 1 molar ionic strength for a 1 molar salt solution. It might seem that a less concentrated solution of sodium sulfate should be less ionic, but if we think carefully, we actually have 1 molar of sodium, since each sodium sulfate would release 2 sodiums, and the half molar of sulfate still has a -2 charge. Since this -2 charge is squared, it plays a larger role in ionic strength. We'd have a 1 molar contribution from the sodium and a 2 molar contribution from the sulfate from 0.5 times 4, and we'd add those together and divide by 2 and find that we have an overall 1.5 molar ionic strength. But ionic strength alone still doesn't explain the differences we see in equilibrium constants. If we think about a solution with charged ions, the area around a positive charge tends to attract additional negative charge to balance it, and the area around an anion, a negative charge, tends to attract positive charge to balance it. Because of this, the full charge of the ion is not completely felt, and it's not completely available for a reaction. We describe this by multiplying our concentrations by an activity coefficient, here indicated as gamma. Together, these are considered the activity of an ion, the concentration times the activity coefficient, which we'd use instead of the concentration alone. By using activities instead of concentrations, we can use constant equilibrium expressions, and we don't have to worry about the changes with ionic strength.